Today we shall discuss about one special type of chemical vapor deposition which is known as the metal organic chemical vapor deposition. In my last class we have seen that there are different types of CVD. There can be, say it can be atmospheric pressure CVD, it can be low pressure CVD, okay, it can be P type CVD, plasma enhanced CVD. There is one type of CVD which is known as the metal organic chemical vapor deposition. As the name implies, there we use the metal organic as the precursors. Now, what is the advantage of metal organic precursor? The advantage of metal organic precursor is that it can be volatile. So, if it is volatile, then to remove that volatile species from the reactor is very easy, because to remove liquid is very difficult, to remove solid is very difficult, solid particles, but to remove volatile species of a reacting agents or of reactants are very easy. So, I shall show you one special type of CVD reactor, which is the MOCVD reactor. Okay. This is a typical MOCVD reactor and we shall discuss about this reactor. Before that, let us see how many different shapes of reactor can have. It can be horizontal reactor, that means when the gas flow is parallel to the horizontal surface of the substrate. Okay. It can be vertical reactor, that means when the gas flow is perpendicular to the surface of the substrate. It can be barrel type of reactor, it can be a rotating disc reactor. Different groups throughout the world have proposed different kinds of shapes for the reactors, and they have their own advantages as well. People have proposed that if you use vertical reactor, see these are the advantages. Some group have told that see if you use horizontal type of reactor, you have different kinds of advantages. So, this is, if you see that in this reactor, you see that this is quartz, this is made of quartz, okay, and this is the inlet through which the gas flows through the reactor. This is the inlet, you see that there is the inlet aperture, and that is the outlet. Through this outlet basically the byproducts and the unreacted gases passes from the reactor to the atmosphere. But care must be taken that before releasing to the atmosphere, if there is any toxic substance, you have to remove that toxicity from the gases or from the byproducts. So, that is the reason that the byproducts or the unreacted gases are passed through a scrubber, SCRABBER. What is a scrubber? A scrubber is basically a heated chamber where charcoal bed is there. Okay. So, there is basically there is a bed of heated charcoal. So, when the gas or the unreacted gases or the byproducts come in contact with that hot or the heated charcoal bed, it burns. Okay. Then the toxicity, it loses its toxicity, then it can be released to the atmosphere. So, it is basically connected to the scrubber. You see that if you see the construction of this type of a reactor, you see that this is the susceptor. This is a graphite block, this is basically a susceptor. This susceptor is placed inside the reactor. Okay. On the susceptor, the substrate is kept. Okay. On the susceptor, this is a susceptor, and you see the shape of the susceptor. On that susceptor, you have placed the substrate. Now, what is the dimension of this susceptor? The dimension of this susceptor is basically 2 centimeter by 2 centimeter. So, that means using this reactor, at the most you can use 2 centimeter by 2 centimeter substrate, not more than that. You cannot use your 4 inch, 2 inch, 6 inch wafer growth using this reactor, that is not possible, because that is a laboratory scale reactor. This is for research purpose, that is not for the production or for any industrial application. So, this is the graphite susceptor on which the substrate is placed, you keep it here. and this is basically placed in a heated chamber. Okay. Or in other way I should say that this susceptor is heated. There is some arrangement in our laboratory, it is the lamp heating. Okay. Lamp is heated and the temperature increases. It can be RF type of heating coil, it can be inductive type of heating coil, it can be laser type of heating coil. Different kinds of heating arrangements can be done. You can use any kind of heating provided you can control it. Why you can control it? Because the temperature of growth is different for different materials. If you use gallium arsenide, the temperature of growth is say 625 degree or 600 degree centigrade. Okay. For indium phosphide, it is say 650 degree centigrade. For indium arsenide, say it is 500 degree centigrade. So, basically for zinc oxide, it is 400 degree centigrade or even less than that. So, from 300, 350 to 700 degree centigrade we use, and it must be very precise. Why? Because the heating must be limited or confined to this place only, not through the other parts of the reactor. So, in that sense you can say that the susceptor is heated and the walls must be cold. Okay? The wall must be cold, that means very confined type of heating must be done. So, that is the reason there are two apertures you see, it is for the circulation of the water. Okay, there is you see that there are two leads through which water circulates, cold water circulates to keep the other parts of the reactor cold. But it is not cold. If the temperature at this place is say 600 degree centigrade, on the other parts it will be 400, 500 degree, not cold. Compared to this portion, it is cold. Okay. So, that is those things you must ensure, and this is another quartz tube, and this quartz tube is placed, you see that there is a groove inside the susceptor and it is placed like this. Why it is placed like this? To measure the temperature of the susceptor, because the thermocouple are inserted through this tube. Thermocouple, how to control the temperature, how you will see the temperature? You cannot measure the temperature by some thermometer, you have to use some thermocouple. Okay. So, this is basically, this arrangement is basically for the typical MOCVD type of reactor, it is placed inside like this type of thing. Okay. And obviously, there will be another tube through which the byproduct or the unreacted gas will pass through this end, and it is made of quartz. One thing you have to keep in mind that if you use oxygen for any purpose inside the reactor chamber, you should not use graphite, because at that temperature the chemistry people should know that at that temperature it will be burnt, carbon dioxide will be formed. So, it will spoil your growth. So, I mentioned earlier that you have to use Inconel or stainless steel or that type of a substrate, okay, through which you can grow good type of thing, because it must not be reactive, because if you use say aluminum, say at that temperature it can smell, it can melt. Care must be taken that it can withstand that high temperature without any damage or distortion. So, that is why Inconel, stainless steel, those are good thing. Another thing is there, it must be thermally conductive, otherwise you cannot measure the temperature. It must be thermally conductive, because you see that it is not in directly contact with the heat, it is placed in some heating arrangement. So, it must be heated. If it is not thermally conducting, then what will happen? There will be no heat increase, there will be no increase in temperature of the substrate or the susceptor. So, that is a stainless steel, you know that it is not a very good conductor of heat. So, generally what happens that you have to wait for a long time. We have used stainless steel susceptor as well, and we have seen that 30-40 minutes are required to stabilize the temperature. Suppose you need 550 degree temperature. So, you have to wait for 30 minutes, 40 minutes. For graphite, it takes just 5 minutes to attain that temperature and to stabilize it. Yes, you have, if you have any question.
Just above the susceptor,
Yes.
temperature is low.
Just above the susceptor, that
this chamber temperature is low.
yeah.
So the decomposed product is the chances of decomposed product would be adhered to this surface.
I know. Actually, what happens? You see that when gas passes through this chamber, a gas mixture passes through this chamber. So, you see there is a volume inside, and the susceptor is made in such a way that it is a slanting type of thing. That means, as you go away from left to right, that is from inlet to outlet, the volume decreases basically, the height above the susceptor decreases, right. You see that the temperature of the upper layer gas is less compared to the lower layer. So, that is the reason that I shall show you that designing a reactor is very important, how to design the reactor, that because you have raised very pertinent question that what will happen, what should be the sticking, what should be the decomposition of the gas. The idea is that it will diffuse, say this is your susceptor, that black block on which your substrate is kept, gas is flowing through this chamber, okay. Gas is flowing. This gas, you can say that this is a boundary layer. Boundary layer means below this layer there will be diffusion of the different chemicals onto the substrate, and there is temperature variation. So, our idea is that it must diffuse, because unless it is diffused from the main gas stream, there will be no reaction, because adsorption must be there, then it will be decomposition, then some nucleation will be formed, and then the layer will be grown. So, now there are some conditions. What should be the diameter of the reactor? What should be the volume of the reactor? What must be the density of the flow gas inside the reactor? So, there are different kinds of consideration, and we shall today concentrate our attention on those things also. Yes, yes.
It also depends on the direction of flow.
Direction of flow is constant here. You see that there must be one inlet and one outlet. You cannot change the direction. What you can do, I think that you are asking that type of a question, that whether there can be other inlets also. Say for zinc oxide, we have encountered one important problem. What is that problem? That zinc oxide, you know that it is very reactive in nature. If you put zinc and oxygen, even if you put zinc in atmosphere, zinc oxide is formed. For that you need not to do any kind of chemistry or any kind of CVD, etc. Not required also. It is very easily zinc oxide is formed, it is very highly active. So, what happens from this inlet, if you put zinc and oxygen simultaneously together, then what will happen? On these parts zinc oxide is formed. Here also it will be formed, here also it will be formed, but on the other parts of the reactors there will be formation of zinc oxide. That is known as the gas phase reaction or parasitic reaction, because that is unwanted. You want that the zinc oxide or any type of material must be formed on the substrate only. So, if it is formed elsewhere on the walls of the reactor tube, that means it is the gas phase reaction, that means your material is wasted. So, cost will increase so far as the industrial applications or the industrial production is concerned. So, what people do, that let the zinc vapor passes through this inlet, and there must be another inlet, say very near to the substrate surface, where through which the oxygen will pass. So, there will be two inlets, Here there is one inlet. This is designed for 3,5 semiconductor. In 3,5 semiconductor, that means gallium arsenide indium phosphide type of material, where that parasitic reaction is not very easily readily available or encountered. This is not very easily formed. Why? Because arsine and phosphine, the cracking efficiency is very high, the sticking coefficient is problem is there, and so only at the hot zone they react. They do not react on the other parts of the reactor. But for zinc oxide or there may be other type of material, because we have not tried all the materials, the gas phase or the cold zone reaction or parasitic reaction is a problem. So, there may be another type of reactor where this is one inlet, there must be another second inlet or third inlet must be there. Through different inlets you are sending different chemicals, so that on the hot zone only the reaction takes place. Okay? Because you are not sending the oxygen here. So, there is no chance of reaction here, only you are sending the oxygen through this portion. So, there will be reaction on this portion, right. So, that is also important thing, that the direction is not the important is that you have to minimize the parasitic reaction or the reaction in the gas phase. Okay. Now, this thing we have considered that how to design the reactor. There are some considerations. One thing is that you see that it may be atmospheric pressure or low pressure. Advantages of low pressure is that it elimination of parasitic nucleation in the gas phase, that we are discussing. That means, if you use a low pressure reactor, then that gas phase reaction can be minimized. Reduction of out diffusion, I have discussed that thing also. What is out diffusion? Out diffusion means diffusion from the substrate, from the surface of the substrate or from one layer to another layer. That means, suppose you are growing aluminum gallium arsenide on gallium arsenide. So, what you are doing? You are first making a gallium arsenide layer, then one aluminum gallium arsenide layer, say this is your gallium arsenide layer, then this is aluminum gallium arsenide layer, then again gallium arsenide layer, because in heterojunction many layers are grown, and that is the advantage of this type of CVD, which is not there for bulk crystal growth. In bulk crystal growth you cannot grow layered structure. Layered structure means which is known as the heterojunction, that is known as the heterojunction in technical terms. It is basically the heterojunction, the junction between two dissimilar semiconductors. Okay. So, now out diffusion means here aluminum from the second layer can diffuse to the above layer or the layer below it. So, that is out diffusion, or from the substrate some impurity can diffuse to the layers, that is the auto doping. When there will be impurity diffusion from the substrate to the layers, then it is doping, auto doping. You are not doping through any chemical, it is automatic from the diffusion of the impurities which are there in your layers or which are there in your substrate, or say if you have not cleaned this thing very effectively, because cleaning is also important. If you how it is cleaned? It is cleaned through aqua regia. You have to put this thing in aqua regia for 24 hours overnight, then you have to boil it in water, then through deionized water, finally it is put in a vacuum to dry it, because you are using 9 and 10 and purity chemicals. So, that is very pure. So, now if your reactors or the susceptors or the substrate is not clean to that level, then what is the use of using 9 and 10 and purity chemicals? No use. So, out diffusion or auto doping may be possible, it is quite possible during the growth. So, this can be avoided if you use the low pressure system. Then improvement of interface sharpness and impurity profile. Interface sharpness means this, say this is the interface, here the interface is between gallium arsenide and aluminum gallium arsenide. Here another interface between aluminum gallium arsenide and gallium arsenide. So, if the interface must be like this, very sharp interface. That means changeover from gallium arsenide to aluminum gallium arsenide is very sharp. Similarly, from aluminum gallium arsenide to again gallium arsenide is very sharp. Okay? It is very sharp, that is step profile. Normally, if this care is not taken, how it will look like? It will look like smeared, it is a smeared out. That means there will be diffusion of aluminum on both the sides, okay, from this side, from that side. So, those things will be there and there will be smearing of the interface. It will not be a step profile like picture. And lower growth temperature can be lowered, thickness uniformity and compositional homogeneity, elimination of memory effect. He has asked me that he could not understand memory effect. Okay. Now, what is memory effect? Memory effect, that is behind the susceptor and sharp corners in the reactor inlet, there may be unwanted materials. Yes, you see that when it is placed, there is a dead volume behind this susceptor. Why? Because gas is coming out from here. So, gas is filling the whole volume of the reactor. Reaction taking place on the front side where there is a temperature, hot zone. So, at the end, at the back end of the susceptor, the gases are not going to react. They are not going to react. Similarly, there are many sharp edges in the reactor. You can see there are many sharp edges on the reactor. So, on those sharp edges, there may be trace amount of material, say aluminum may be there. So, when you undertake this growth, that means from aluminum gallium arsenide to gallium arsenide, what will happen? This trace amount of aluminum will be there inside the reactor chamber, because intermediately you cannot clean the reactor unless the whole growth is finished. When the whole growth is finished, using aqua regia you can clean this thing, so that there will be no aluminum, no gallium, no arsenic. But when you are preparing the layers, so during the growth you cannot clean this reactor. Okay. So, there may be some trace amount of aluminum or other, here we are taking the example of aluminum, it can be different types of materials also. So, those can be trace amount of those materials can be there in the behind the susceptor and the sharp corners in the reactor inlet, which cannot be removed easily. Okay. So, how it can be removed? It can be removed by low pressure, because at atmospheric pressure it cannot be forced to be removed from this reactor to the scrubber. If it is a low pressure type of thing, then continuously it is evacuating, it is sucking from what are there inside the reactor. So, the memory effect can be reduced using low pressure reactor, not atmospheric pressure reactor, because there are some chemicals which are very additive in nature, like aluminum. Removing aluminum is very nasty job. Even on the MOCVD reactors from the different gas lines, if you pass aluminum through those gas lines, that the whole line will be blocked by the aluminum scales. Okay. That is the problem with the zinc oxide also. So, that is basically the memory effect. Memory effect means you see that this aluminum can be moved to the second layer. So, though it is your gallium arsenide layer, some amount of aluminum may be incorporated in the second layer or third layer or the successive layers. So, that is the memory effect. During the growth of sharp heterojunction and steep doping profile, by switching a flow with another chemical composition, the original composition is still present, memory, in the vortices and trapped gases. The slow out diffusion from these parts will smear out the doping or the heterojunction profiles, can be eliminated by rapid evacuation, that means working at low pressure. Okay. So, memory effect is one important thing which can be considered for this type of reactor. So, you can design a reactor where the memory effect can be less. So, people have arrived at this reactor after many R&D. Why the shape is like this? Because of those considerations only. People have tried with different kinds of shapes. And it is a horizontal reactor. What are the advantages of horizontal reactor? The advantages of horizontal reactor is that uniform gas flow over a slightly angled acceptor. This is 7 to 15 degree, the angle is 7 to 15 degree, because it has been proved that the gas flow will be uniform if there is a certain slanting of the susceptor because of the velocity problem that we shall come. Uniform deposition, reactants are depleted from the gas flow, low cost, simple design. What is the meaning of this term? Reactants are depleted from the gas flow. See, this is the gas flow and the reactants are depleted means they are diffusing to the substrate or to the susceptor surface, right. So, that is the meaning of this term, the reactants are depleted from the gas flow, low cost, simple design, etc. Yes. Now, very important aspect is that for very good CVD reactor, you have to consider two important aspects. One is that the gas flow must be laminar flow, not turbulence. The opposite of laminar is turbulence. You know what is turbulence? Yes, that is random.
The flowing of water in the field.
The flowing of water in the
Field.
basically during flood. The flow of water in the river during flood, it is basically turbulence. Or you will find that turbulence in the big rivers also, in Ganges, in big rivers also, there are always some turbulence. But we need laminar flow. Laminar flow means the flow will be in a particular direction, free from any distortion. It will start from one point and it will take the same path and will reach the same point. Which will take the same path? The gas molecules. In our case, it is we are talking about the gas molecules. In gas molecules, all the chemicals are embedded. Okay. So, we are concerned about the flow of the gas inside the reactor. Now, for laminar flow, we have to take the help of Reynolds number. What is Reynolds number? Reynolds number is given by rho V bar d by eta. What is rho? Rho is the density. I have given the unit also, kg per meter cube. It is the density of the gas. In this case, it is basically a mixture of gases. It is not a single gas. It is not a single gas. Suppose if you use one single gas, say silane, then it is the density of silane. If you use say diethyl zinc and oxygen, then it is a mixture of the vapor of diethyl zinc, the oxygen gas and the carrier gas which are carrying those vapors into the reactor chamber, because the vapor pressure must be high obviously, but at the same time vapor pressure cannot go of its own to the reactor site. You have to carry those vapors by some carrier gas. It may be nitrogen, it may be hydrogen. We have discussed those things also in detail. When we shall use nitrogen, when we shall use hydrogen, why hydrogen is preferred. But say for zinc oxide we cannot use hydrogen, because it can be, what is the problem with hydrogen in zinc oxide growth? Because oxygen is there, so it may be inflammable. Because oxygen is there, and if you put hydrogen, so there may be inflation. So, you see that it is the density rho, V bar is the average flow rate of the gases, d is the diameter of the tube, eta is the dynamic viscosity. And if you make a reactor, say you are making a reactor for silicon growth, let us take an example for silicon growth. So, you can calculate the rho of the gas mixture. What would be the gas mixture? Gas mixture will be silane and hydrogen. So, take silane and hydrogen and calculate the density. It is available in the literature. Then viscosity is also available in the literature. V bar is the average flow rate and d is the diameter. So, you have to work out with V bar and d. You have to work out with V bar and d to obtain Re, which will be less than 100. Because if Re is less than 100, that is a thumb rule. It can be 97, it can be 120, but normally if it is less than 100, the flow regime will be laminar, it will not be turbulence. If Re is greater than 100, then it will be turbulence. So, that means your diameter of the reactor, okay, this is the diameter of the reactor, and your gas flow rate, what should be the flow rate? It is 6 liter per minute, 5 liter per minute, 100 cc per minute. So, those things you have to work out, so that the Reynolds number becomes less than 100 and the flow regime is laminar. Okay. So, there are two considerations, one is the Reynolds number to make the flow laminar, free from turbulence, and another we shall introduce the Rayleigh number, which will give you the diffusion, not the convection. Okay. The flow must be laminar, and also inside the reactor it will be diffusion, not the convection. Okay. So, now what are the characteristics of laminar flow? The characteristics of laminar flow is that velocity at a fixed position is always the same. Velocity at a fixed position is always the same means, say velocity at x equals to t or x equals to x dash inside the reactor, it is always same throughout the growth. If you grow for 1 hour, or if you grow for say 20 minutes, or if you grow for 10 seconds, the velocity at a particular point is always same. Each element travels smoothly along a simple well defined path. Each element travels smoothly along a simple well defined path. Each element of gas molecules. That means, in the gas molecules, what should be the molecules? One type can be, say for 3,5 semiconductor growth, it can be the molecule of the trimethyl indium. Say you are growing indium phosphide. Say you are growing indium phosphide. So, for indium, what is the precursor? Trimethyl indium. That is why it is organometallics. Trimethyl means it is a organometallic, trimethyl indium, and for phosphine. So, vapor of trimethyl indium plus vapor of phosphine. Phosphine is in the gas state. So, there is no question of forming vapor plus hydrogen, because hydrogen is carrying those things. And if you dope it say N type, then additionally it will be hydrogen sulfide or silane. So, trimethyl indium, phosphine, hydrogen sulfide and hydrogen, right, for indium phosphide N type of growth. If it becomes indium gallium phosphide, then trimethyl indium for indium, for gallium it is trimethyl gallium and phosphine. Then it will be hydrogen as well, and if you dope it p type or n type, the dopant molecules will also be there. Okay. So, each element means considering all those things travels smoothly along a simple well defined path. Each element starting at the same place follows the same path. For Re high, that means if the Reynolds number is high, flow becomes turbulent. Flow becomes highly random with rapid irregular fluctuations of velocity in both time and space, because as the time elapses it will be, there will be fluctuations, and also at different points of the reactor chamber it will be different. So, there will be turbulence. So, care must be taken, that means you must design your reactor in such a manner that there will be no turbulence, the flow will be laminar flow. Okay, it is clear. Another important aspect is the diffusion and convection, because you see that if you see this view graph, this is the average gas flow inside the reactor and it must diffuse. Why there will be a question of convection? The question of convection is that the density of the gases inside the reactor is different, as you mentioned, because of the temperature gradient in the reactor chamber, the density is different. So, if the density is different, then what happens? Convection happens. Okay? Like the storm, how storm originates? When the air from the earth's surface, no, it becomes hot and it moves upward. Then to fill that gap, cold air from the surrounding regions come to fill that gap. So, there will be a convection type of thing. So, here there is a chance, since the temperature variation is there at very near to the susceptor, you see that there will be more heat than the top layers. So, the difference of density will be there and there may be some convection, obviously there may be some convection. So, to avoid that convection, we have to calculate the Rayleigh number. Rayleigh number of reactor flow, it is given by G, which is known as the acceleration due to gravity or gravitational constant. Alpha is the coefficient of thermal expansion, Cp is the specific heat, rho is the density, H is the free height above the susceptor, and delta T is the temperature difference between the susceptor and the reactor wall. There will be a difference of temperature between the susceptor and the reactor wall, and it is in the numerator. In the denominator there will be the viscosity, eta and the thermal conductivity, right. So, this is the equation for the Rayleigh number. That means, you can calculate the Rayleigh number using these parameters, and for any gas or gas mixture you can calculate the parameters, or the parameters are available in the literature. So, if you put the values, you can calculate what should be the value of R A. What should be the value of R A? Here you see that R A proportional to rho square. Here, if the other things are constant, then R A is proportional to rho square. In the earlier slide, it is R E proportional to rho. R E proportional to rho, for that means the Reynolds number is proportional to density, and Rayleigh number proportional to density square. So, most important consideration for the reactor design is the variation in density, because you know that the variation in density will be there because of the temperature gradient. So, that is the most important factor. You have to play around that thing only, then only it is possible to design a very good reactor. It is not true for only the MOCVD, it is basically for any kind of CVD reactor. Okay? Because in almost all the CVDs you are sending some vapor or the gas or the chemicals in the gas phase. So, they are diffused onto the substrate and adsorption is taking place, followed by the reaction. So, for any CVD you have to play with the reactor, because the gas is not very important, gas is there. In these days you can procure any kind of gas, any kind of chemicals with very high purity. That is not the problem, problem is with the good reactor. If you have a good reactor, then only it is possible to grow very good materials, otherwise you cannot do. And here you see that there is another important term which is the delta T. This delta T is the difference in temperature between the susceptor and the reactor wall. Okay. So, that is also important, because to keep the Rayleigh number as a particular value, delta T must also be optimized. Now, see what should be the Rayleigh number to obtain a diffusion, because we do not want convection, remember. We do not want convection, because in convection you do not have any control. You do not have any control. You have to make diffusion, because if the chemicals from the main gas stream diffuse very efficiently, then the growth will be uniform, the growth rate will be high. Otherwise, what will happen? If the diffusion does not take place properly, the growth rate will also be very less. More and more diffusion will take place, more and more thickness of the layer will be grown. So, now the Rayleigh number will be less than 1700, the gas is stable, and greater than 1700 free convection occurs. Okay, you do not have any control, the convection will be there. Okay, it affects the mass transfer, growth rate and homogeneity, right. So, what is mass transfer? Mass transfer is the diffusion of the chemical pieces from the main gas stream to the substrate, and it must be, the mass transfer will be a whole mass transfer. That means, all reactants, suppose if you consider that this indium phosphide will be grown. So, trimethyl indium and phosphine, both molecules must transfer to the substrate site, not that only TMI diffusion will be sufficient, no, because unless the same quantity of phosphine is there, there will be no reaction. Okay. So, one thing is the mass transfer, and a growth rate, as we have discussed, that if the diffusion takes place in an improper manner, then the growth rate will be very less, and the homogeneity will not be there. Homogeneity means it is the uniform layer. there will be no deficiency of indium or phosphorus. It is a homogeneous film of indium and phosphorus, indium phosphide say. Now, convection, the origin of convection that we have discussed, it occurs between hot substrate and cold reactor wall. Only then there will be convection, if there is a temperature gradient in the mass in the gas flow. Convection is due to action of gravitational field on the density variations associated with the temperature variation. That is the textbook thing that you all know, that since there will be a variation of the temperature, so the density will be different. In some places it will be rarer, in some places it will be denser, and when it when the gravitational force is there, so it will move like a convection. Okay, so that, so what we think, or what we see, that Rayleigh's number and Reynolds number, it is Rayleigh and it is Renault. These two things we have to consider. So, suppose if you now try to develop a reactor for a CVD for any material, say for a new material, say for nitrides, there is immense scope for nitrides, there is immense scope for ceramic thin films. Suppose you want to make with some CVD reactor, then you have to consider the design of the reactor in this manner. First you have to calculate, or you must know the different parameters of the gas flow. Then you have to calculate the Reynolds number or the Rayleigh's number, and then you have to finalize what should be the diameter of your reactor, okay, what should be the angle, what should be the flow rate. So, those things we have to optimize. So, in essence we can say that laminar flows free of convection should exist by using a horizontal reactor, working at low pressure and decreasing the reactor diameter. So, decreasing the reactor diameter, how you decrease the reactor diameter? The reactor diameter can be decreased if you make the susceptor inclined. If you make the susceptor inclined, then what effectively the diameter reduces. It is like this. Say this is the uniform tube or the reactor. You want to make the diameter less. The effective diameter become less. Effective diameter become less because here the diameter is say D1, here it is D2, here it is D3, here it is D4, right. So, the design principle is based on those facts that you use a horizontal reactor, you use low pressure and decrease the reactor diameter, then you can ensure laminar flows free of convection.
Sir, which diameter we will take in that case?
Which?
Diameter.
In the reactor.
Yes, sir.
In this reactor also, if you see that the diameter is gradually decreasing. Yes. So, inside the reactor where the actual growth takes place.
On the susceptor.
No, here you see that in this pictorial diagram, the diameter of this whole thing, this is the diameter, actual diameter.
Yes.
Now, putting this susceptor in an inclined manner means you are reducing the diameter. So, diameter basically inside the tube, do not think that the diameter of this thing, it is basically the cover of the thermoelectric wires. Okay, this is basically the casing of the thermoelectric wires. This has nothing to do with the growth or the reactor. Okay, it is basically a cover of the thermoelectric wires to measure the temperature, because we are speaking, we are telling that the temperature is 800 degrees centigrade. So, how to measure the temperature, how to stable the temperature. Now, no temperature gradient should be present across the susceptor. Eliminate the memory effect. How? By the geometry of the reactor is such that no vortices can develop. Vortices means the dead space behind the susceptor. No dead volumes are present inside the reactor, that means different edges. Different edges. Here also you can see, if you minutely check this reactor, you will find that there are many edges inside. And elimination of sharp corners in reactor inlet, where the laminar flow can go by without having a strong interaction, and also behind the susceptor. The flow must be smooth. If there is any edge or some uneven surface, so that means the flow will be obstructed. So, there will be some obstruction. If obstruction takes place, then there will be turbulence. Any obstruction will be turbulence. So, this is a different epitaxial method we have discussed earlier also, that is LP, VP, MB, MOCVD. In the next class we shall discuss about this MBE. Now, what are the advantages of MOCVD growth? It is, that means advantages over the other CVD. Okay. Here the material can be grow at atmospheric pressure, one advantage. Second advantage is that the precise control of composition, doping and thickness. One is composition, second is doping, and third is thickness. You can very precisely control. Precisely control means plus minus 1 angstrom. Plus minus 1 angstrom thickness you can control. For doping, it can be 2 into 10 to the power 17 or 2.5 into 10 to the power 17 or 3 into 10 to the power 17, you can precisely control. If you want it to, it should be 1.8 into 10 to the power 17, it is possible using MOCVD. Very precise control. In some device applications, in our later part of this class we shall show, of this course we shall show that in some cases you need the doping very precise. And flexibility, scalability into larger commercial system, that is possible. If you can grow with say 1 centimeter by 1 centimeter substrate, it can be grow by 1 4-inch substrate as well, because it is basically you are playing with the gas. If it is liquid or if it is solid or it is a physical type of thing, then it was not possible to cover the whole surface. Since you are using the gas, so the whole surface can be covered. So, now in MOCVD what is the reaction? Reaction is that this R3X plus YH3, what is R? R is an organometallic compound. What is X? X is group 3 element, that means gallium, indium, aluminum, etc. Yes, or actually organic radical basically. Rx is organometallic, R3 is organometallic. So, you can say that it is organo radical or organo yes, organic radical, it is known as organic radical, methyl, ethyl, butyl. So, these are the organic radical. So, R3X is the organometallic, and what is Y? Y is group 5 element, that means phosphorus, arsenic, antimony, etc. So, if this is the case, here you see that it is the reaction will give you XY plus 3RH, 3RH, right, 3RH. So, that is the organometallics. And if you take one example, you see that trimethyl gallium CH3 gallium plus ASH3 arsenic you will get gallium arsenic plus CH4, that means methane. So, methane is the byproduct. That is the problem with the organo or MOCVD. That is the problem, means it is very toxic, it is inflammable, arsine phosphine is involved. So, care must be taken. Okay. So, in a nutshell we can say that there are some advantages of MOCVD, but the problem is with the design of the reactor and the toxicity of the chemicals associated with the MOCVD growth. Thank you.